Um, so today we're going to continue thinking about our quadratic residues, and there's an important principle which we're going to encounter today, which is quadratic reciprocity. Okay. This lecture will be a little bit more descriptive, investigatory, less kind of close technical proof work. If you've been flicking through the notes, you'll notice there's a number of theorems yet to come, a number of quite technical arguments still to come. We'll begin those next week. But we'll take a little bit of break from that close technical work and do some kind of looking ahead, investigative work here today. Okay, so recall we've got some basic ideas. P is an odd prime bigger than 2. NP is our Legendre symbol, plus 1, minus 1. Depending on n, if n is a quadratic residue, mod P. And not a quadratic residue, mod P. Okay, so the Legendre symbol indicates plus or minus 1, whether or not the n is a quadratic residue. Remember, being a quadratic residue means being a square. Quadratic residue mod P means you are a square, you're the square of something mod P. We've applied the, we had Euler's criterion, which that NP is always congruent to n to the power P minus 1 over 2 modulo P. Okay, I reviewed this yesterday, so I won't spend time reviewing it much again. And we've seen applications of this which settled the residue status of minus 1 and 2. We've seen applications of this to settle some special cases. So minus 1 modulo P, we completely understand when this is a residue and when it's not. It's a residue exactly when the prime number is congruent to 1 mod 4, and it's a non-residue exactly when the prime concerned is congruent to 3 mod 4. Of course, 1 or 3 mod 4 are the only options for an odd prime number. It can't be even, so it has to be either 1 or 3 mod 4. And the 2 mod P, again, you completely understand that, and that's determined by the residue status of P modulo 8. That one we proved yesterday. Spent the whole of yesterday proving this argument, proving that result. And we're going to encounter this principle of quadratic reciprocity today. I'll remind you, if we try and evaluate NP based on the prime factorization of n, so n is a prime factorization, it's a product of a load of prime powers. N is a product of a load of prime powers for various different prime numbers, P1, P2, up to PR. Well, if we try and evaluate what the Legendre symbol of NP is, well, it develops like this. So none of these PIs are equal to P. And we'll assume we're dealing with an n which is not divisible by P. Now, I showed you this little sequence of equations before. I'll just remind you of them. So we're going to see what we can do at the moment with developing this. Just briefly, any points to clarify just on the quick review? I know I just chucked a lot of stuff at you, but it is stuff we've covered in the previous lectures, and I just like to just bring it to the front of your minds again. So anything there I could clarify? So what I'm thinking about now is, so we've got some specific, we know the residue status of minus 1, we know the residue status of 2. Well, returning to the general question, what's the residue status of n modulo P? We're going to work off the fact that n is a prime factorization. So the Legendre symbol NP is the Legendre symbol of N with P. Now, one of the first proper things we proved was how residues operate under multiplication. And what that meant was that the Legendre symbol, when you consider the Legendre symbol as a function on the first argument here, it's multiplicative. So if I've got a big product here, it's going to turn into the product of the individual Legendre symbols. So the product pi operator comes out to the front, and this exponentiation floats outside as well. So that's since this, as a function on the first variable, is multiplicative. That was one of our earlier lemmas. Theorem 8.3. Okay? So we've applied that here. It's a multiplicative thing. So this big product here, it all floats outside. You got a big product of many individual Legendre symbols. Okay? One for each prime that features in the prime factorization event. Then you remember that, well, these individual Legendre symbols here are either plus or minus 1. So what you've got here is just a big product of powers of plus or minus 1. So anytime there's an even power here, we can just ignore the value, because if this is plus or minus 1, when you raise it to an even power, it always gives you plus 1. So the only thing you need to check or worry about, the only thing you need to record is this product when the alpha I is odd. Right? But then you're going to have plus or minus 1 to an odd power. Well, that's just going to be the same as the original plus or minus 1, whatever it is. So it just comes down to a product of these Legendre symbols, but only over the product where alpha I is odd. Okay? So not necessarily over each and every one prime pi that divides n, only taking this product over those primes that occur to an odd power in the prime factorization event. Okay. So this is how far we can take the evaluation using some of the basic facts we know about the Legendre symbol. It's multiplicative, and it's either plus or minus 1, and then we're taking powers of plus or minus 1. But we kind of run into a halt now. But this shows you that the general question of what is n modulo p, what is the status of n modulo p, boils down to understanding what's the residue status of one prime modulo another. Yeah? If only we could answer these questions, we then know how to evaluate this. Can everybody appreciate that? Yeah. So the general problem of residue status of n mod p, what is it? Is it a residue? Is it a non-residue? Is this Legendre symbol plus 1 or minus 1? Well, if only we could understand these ones to know whether these are plus or minus 1, then we could just count the number of minus 1s that we have, and that would tell us if it's odd or even. That tells us whether the whole product comes out as plus 1 or minus 1. The general problem of evaluating NP, provided you have the prime factorization of n, which theoretically we do, the general problem of evaluating NP boils down to understanding, well, let's just adopt this notation. PQ now, where P and Q are both primes. So this becomes the main question now. What is the value, what is the residue status of one prime modulo another? And we're in the dark at the moment. There's no reason to expect any kind of clear, simple answer from what we work to at the moment. Okay. Now, the principle of quadratic reciprocity, which we're going to discover now together, is now some people have referred to this as a little bit spooky or mysterious, a spooky connection between PQ and QP. So whether or not P is a quadratic residue modulo Q, and the different question, whether or not Q is a quadratic residue modulo P. At the moment, these are two separate questions. And we have no reason to believe that there's any connection between the two. But there turns out to be an extremely systematic, an extremely direct connection between the two. Now remember, each of them individually, this is either +1 or -1. This is either +1 or -1. So, they've got a 50-50 chance of being equal, you might guess from the start. It turns out, in general, they've got a 3/4 chance of being equal, and only a 1/4 chance of being different. And that's what we're going to discover now together. Okay? So a spooky or just a unexpected connection between these two. Any clarification that I could give before I'm going to switch to the computer now and do some example calculations to discover what this connection is. Was there any clarification I could give on any of this discussion? So the main thing to appreciate is how the general question boils down to understanding the residue status of one prime modulo another. If only you could magically answer all these questions, i.e. know whether these are + or -1, then you would know the value of this. Okay. Now, so I've got some investigations prepared here. I'll put it up on the Moodle area. It's a link to a Sage worksheet. Okay, steady down. Right, so the first thing we're going to do is we're just going to calculate a load of them. Okay, so thankfully, we're making use of an inbuilt function in Sage here. There's a function called Legendre symbol. And you give it 2 arguments, and it does what you expect. It evaluates the Legendre symbol n modulo p. Okay, so it tells you whether or not the first argument is a quadratic residue modulo the second argument. Okay. So let's just look briefly at this code. What I'm doing here is I'm setting an upper limit n to be 200. I'm creating here a list of points PQ, where P is every prime between 3 and n, and Q is every prime between 3 and n. But I exclude the case if not P equals Q. So this is all the pairs of distinct primes between 3 and n. Every possible pairing of primes you can do between 3 and n. And then upper limit I've taken is 200. And then for every pair in the list of points, if the Legendre, so x0 is the first is P, x1 is Q, the first entry of the list, the second entry of the list. For every pair in points, I worked out what the Legendre symbol. If it's +1, I'm going to add to the plot a blue point. And if it's -1, so the else there, if this isn't +1, it must be -1. So it's a Legendre symbol. If the Legendre symbol of the P mod Q is -1, I plot a red point. And then I just plot all these points. What we'll get is a grid of colored points. Okay, they're going to be every blue point. The blue point at coordinates PQ says that P is a quadratic residue mod Q. A red point is going to mean P is not a quadratic residue modulo Q. So I get this plot here. So it's what you expect. It's a cloud of red and blue points. What was it? Red for, keep forgetting the same. Blue for +1, red for -1. So every blue point says that P modulo Q is a quadratic residue. Every red point says that P modulo Q is a quadratic non-residue. So what the early mathematicians didn't have, so I think it was the number of mathematicians discovered this principle independently. Of course, they didn't have Sage to work with. This was back in the probably 19th, 20th century, 19th century, I'm sure, maybe even 18th century. But they could work, doing hand calculations, working up to the primes, up to 200 wasn't beyond them, of course. Okay, so they could have effectively done this and looked for these patterns. What kind of pattern might we be looking for there? Or is there some query or question you might ask of this plot? Given what I've already said leading up to that. So I said leading up to now we were looking for a connection between the residue status of P mod Q and Q mod P. So PQ and QP, those are the points that are opposite each other across the main diagonal. Yeah. So there's this question is this plot symmetric? Is this plot symmetric? So that's going to be one question. The one question is there more blue dots than red dots? You might ask that question as well. Is the chances of one prime being a residue modulo another one, is it 50-50? I think it is. I think if you count up all the red and blue dots there, you'll find they're roughly equal in number. Is this symmetric? Sorry, the fact that it's vibrating. The whole building is always vibrating, so can't get beyond that. But is this symmetric? Well, you bet it. Yeah, no, it isn't symmetric. So you'll find examples. So this pair here are opposite each other. So this is PQ and this is QP. Yeah, the main diagonal goes up there. So these two points have opposite color. So it's certainly not symmetric. But we got two reds, two blues, two reds. Okay, different. But again, two reds, two blues. Okay, different. Two red, two blues, two reds, two red. It's sometimes the same across the diagonal, sometimes different. But it seems to be the same. This seems to be the same more often than it's different. So I'm looking at the points closest to the main diagonal here. Two reds, two blues, two reds, two blues. Okay, different. But two reds, two blues. Okay, different. Back to two reds, different. The same, the same, the same, the same, the same. That's the same, the same, the same, different. So sometimes the same, sometimes different, but the same a good deal more often, right? When you look close, okay, that's looking at the ones closest to the diagonal. You can make the same comparisons, for ones opposite each other a long way from the diagonal, of course. You can also look closely along rows and columns. you choose the last column and the last row, you'll see they're different. The last column starts off blue, blue, red, blue, blue. But the last row starts off red, blue, blue, red, blue. You know, so there's no, they're not the same. Yeah, question?
So the reason that there's like a big gap like in that column.
Well, there is. Why is there a gap there? Well, there's no primes in this gap. Remember, I was only picking up point that the code only asked for the P and Q being primes between 3 of them. So yeah, there's a thick gap here and here because there's no primes in this range. And you know, there are moderate gaps the other places. The dots that are right beside each other, you know, so this first one is the prime. The first column is located at P equals 3. The second column is located at P equals 5. Then P equals 7. And then you got a gap because 9 is not a prime. So there's no dots at column 9. But then there is at 11, there is at 13, there isn't at 15, there is at 17, there is at 19, there isn't at 21, there is at 23. But 25 and 27 are absent, but then 29 and 31 are there. So we're only seeing them at the prime. So this is a large prime gap here that you encounter. Okay, good question. So the last column and the top row are different, but look a bit closer. Look at the second last column and the second top row. Well, if you look at the second last column and the second top row, remember, they are reflections of each other. Yeah. So every point here is coordinates PQ, and it's got a partner point in the reflection across here, which is coordinates QP. But you'll see the sequence of dots is exactly the same. So the second last column goes red, red, blue, red, red, red. Red, red, blue, red, red, red. And you inspect along, you'll see it's exactly the same. You'll find many other columns there that are symmetric with their reflected rows. But also many columns which are different to their reflected rows. Okay? So we're seeing some similarities under reflection and some differences. But remember, now, but by random chance, you'd expect 50-50 chance of them being the same across the diagonal, of any 2 points across the diagonal being the same, 50-50 chance. But we've already seen when we examine the ones closest to the diagonal, they're the easiest ones for our eyes to pick out at a distance. Much more frequently, we have the same status across the diagonal than different. So there seems to be a bias going on. So now that we've picked up on this issue, are they the same across the diagonal or not? We can investigate that, okay? So I want to redo the plot now, but instead of plotting red for +1, blue for -1, now I'm going to plot, you know, something to represent the same value of the Legendre symbol across the diagonal and something to represent that they're different. So we'll go back to the code here. So I essentially redo the plot. But if you look at the code is slightly different. This time I'm going to plot black circles, but I'm going to have an unfilled circle to say that the Legendre symbol PQ is equal to the Legendre symbol QP. So the 2 points have the same status, either they're both residues or they're both non-residues modulo each other, then I'm going to have a white unfilled circle. If they have different status, if one is a residue modulo the other, and the other is a non-residue modulo the first, then I'm going to fill in the circle. So this pattern of points will reveal whether or not we have symmetry across the diagonal, and exactly where we do have symmetry. So you can, okay, so the code is we gather these points. We get the Legendre symbol of x0, x1, that's L1. We get the Legendre symbol of x1, x0, that's QP, and store that in L2. And if L1 is equal to L2, I plot a fill equals false, an unfilled circle. If the two Legendre symbols are equal. Otherwise, if they're unequal, i.e. one is the negative of the other, remember they're plus or minus 1. If they're unequal, I plot a fill equals true, so a filled circle. I've slightly changed the set of points. Because the points I'm plotting are representing whether the Legendre symbols are the same across the diagonal, I'm only going to plot the lower triangular part. Because the plot that this produces, if I extended it across the full square, the plot would be symmetrical. Because the condition of whether the circle is unfilled or filled depends on whether the two Legendre symbols are the same or if they're different. So what you see on one side of the diagonal will just replicate what you see on the other side. So this produces this plot here. Okay, so I'm just looking below the diagonal. So here, this unfilled circle says that this P modulo this Q, it's not saying whether or not it's a quadratic residue, but it's saying it's got the same status as Q modulo P when you look at its reflection across the diagonal. So that white circle means that this P modulo that Q, whether it's a residue or a non-residue, it's the same status as Q modulo P when you look at its reflection across the diagonal. Okay. So a unfilled circle means its partner, where you switch the coordinates, has the same residue status. A filled circle indicates that the partner, where you flip the coordinates, has the opposite status. Now, the first thing you notice when you're looking at this is far more unfilled than filled. There's about twice as many unfilled than filled, right? As we noticed in the previous plot, sometimes a whole column is exactly the same as its reflected row. So that's replicated here. Remember, the second last column is all white, is all unfilled, because all of these points here, when you swap the coordinates, you've got the same residue status. You see there are many other columns which consist of all unfilled circles. Now look at one of the columns where it's a mixture. So for instance, the last column. Okay, so we got a mixture of black and white dots. Now remember, we're just looking at odd primes. So I've only got positions at all odd numbers on the graph. And the places where I'm skipping is where that odd number is not a prime. Yeah. So this is the big gap here where there's no odd primes in this range here. Okay. But if you sit and stare at this plot, what you notice is that the black and white dots are alternating if you put in an alternating color dot at the non-prime positions. I'll say that again. Anywhere where you do have consecutive dots, they alternate. The black, white, black, black, white, white, black, white, black, white, black, black, white, black. So anywhere you've got immediately neighboring dots, they alternate. You never have two white dots beside each other. You never have two black dots beside each other. Now, we don't have dots at every position because not every position is prime. But if you did put in a colored dot at every position and you alternated it, you see that would fit in exactly with what's there at the prime positions. So if you step up here and go black, white, 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 black. Okay, you're naming colored dots at non-prime positions, but where you pass through the prime positions, you're exactly agreeing with what's there. Okay. So that's, and we see that between the primes between 0, 1, and 200. If you extended it across any range, you'd see it being replicated as well. So there's an alternating thing going on there. Then you come and you ask, well, some of the columns are all white, some of the columns are a mixture. Whenever we've got two columns exactly neighboring, one is all white, the other is a mixture. See, these are neighboring columns. One is all white, the other is a mixture. One is all white, the other is a mixture. All white, a mixture. All white, a mixture. All white, a mixture. So anywhere where there's neighboring columns, one is all white, one is a mixture. If you did the same exercise, remember, you've only got a column at the prime positions. If you did the same exercise to add in a column, remember the status of a column is all white or mixture. If you put in the missing columns and you alternate the status, you'll see you've got this exactly alternating pattern. You've got mixture, all white, 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 mixture. So I'm naming columns where there aren't any, because those positions aren't prime. And I'm alternating my all white mixture classification, but it exactly agrees with the prime columns that are there. So what we've discovered here between 0 and 200, for the primes between 0 and 200, we've got an exact alternating pattern of all white columns, mixture columns, alternating across. And in the mixture columns, we've got an exactly alternating sequence at all the odd positions, which only shows up at the prime positions, but we've got an exactly alternating sequence of white, black, white, black, white, black. So we've got extremely systematic behavior here, which we conjecture extends across all forever. It always occurs at the prime positions. Now, the plotting positions are the odd numbers. Yeah, we only actually plot something when it's got prime coordinates. Okay. Now, if you've got an alternating pattern across all of the integers, like your odd even pattern, odd number, even number, odd number, even number, that's associated with mod. That's a mod 2 pattern. If you've got a feature that alternates across the integers, all of the integers, it's a pattern which is going modulo 2. Yeah. It just depends on whether you're 0 or 1 modulo 2, whether you're even or odd. Here, we're only talking about the odd positions, but we've got an alternating pattern across the odd positions. So that means we've got a modulo 4 pattern. The odd positions are 1 and 3 modulo 4. So this feature of being an all white column or a mixture column, and in a mixture column, whether you're white or black, it's all alternated. So it's all a modulo 4 pattern. So if you take this alternating pattern that you've noticed, and you sit down and think how it's expressed modulo 4, what you discover is the principle of quadratic reciprocity, which was discovered. I've got some notes on the historical, or do I? Yeah, at the bottom of page 65, there's a few notes on the historical when it happened. So, and a few people, Euler, Gauss, a few Legendre, a few people discovered it independently. But this is what you end up saying. So whether PQ is equal to QP, or whether they're opposite. So this, if PQ is equal to QP, that's the presence of an unfilled circle. If PQ is different from QP, i.e. it's got the one is the negative of the other. Remember, each of them individually are +1 or -1. So if they're different, that means one is the negative of the other. That's where you've got a filled circle. And it's a mod 4 pattern, right? So you only have a filled circle. You only have a black circle, which indicates opposite status. That only occurs when both of the primes are congruent to 3 modulo 4. Otherwise, the residue status of P mod Q is the same as Q mod P. So this is the principle of quadratic reciprocity. Saying it's spooky, or it's just a funny way of saying it's just unexpected. Before now, we would have had no reason to expect that there should be a connection between the residue status of Q mod P and P mod Q. But when you do like calculate enough examples, lay them all out, study the patterns closely, this pattern emerges. Okay? So this pattern, this mod 4 pattern, is exactly this alternating status pattern we've discovered across these odd positions. Now, so what? Well, this gives us an important new property of the Legendre symbol, which will allow us to calculate any Legendres. So here's how it goes. First of all, so I'm going to show you an example now of how we might calculate an arbitrary Legendre symbol. We'll return to this in future weeks because it is important. But first of all, any questions just about all of that? So it's rather than just having this fall out of the sky onto your lap, I just want to indicate how you would reasonably go about discovering this, or how these mathematicians a few hundred years ago, how it was that they noticed this pattern. And of course, they noticed it long before they'd had a fully rigorous written down proof of it. You can conjecture that it always happens. I haven't proved it, of course. I've only proved it happens for the primes between 0 and 200. There's an infinite number of primes. We've known that since the ancient Greek. So we conjecture that this principle applies always. Of course, we need a proof of it. Yes, question?
Why did you get 3 and 4? So the mod 4 and the 3. Why didn't you just pick those?
Well, I didn't just pick them. That's what's going on here. So the first thing to understand is that it is a modulo 4 pattern. Okay, as I said, if you've got something that alternates at every integer position, that's a mod 2 pattern. It's at one status at all the things congruent to 0 mod 2. It'll have the other status of the things congruent to 1 mod 2. But now the positions here are just all the odd integer positions. Okay, because you're only going to see a prime number at an odd integer position, except for 2, which we're not doing. So my plotting positions here, and sometimes I don't plot because it's not a prime. My plotting positions are just the odd integers. So if you've got something that alternates across the odd integers, so you got one status at 1, another status at 3. You reach the same status at 1 at 5, and the same status at 7 as 3. So something that alternates across the odd positions. That comes down to the value of the position modulo 4, whether you're 1 or 3 mod 4. Yeah? 1 or 3 mod 4. Now, when you look at where the columns are positioned, you'll notice that the column is all white at every position that's congruent to 1 mod 4. Okay? So if the P is congruent to 1 mod 4, it's an all white column. If the P is congruent to 3 mod 4, it's a mixture column. And within the mixture column, you've got half white, half black. You've got white at the positions that are congruent to 1 mod 4, black at the positions congruent to 3 mod 4. So it's only when both those conditions hold, when you're at the column at position 3 mod 4 and at the row at position 3 mod 4, that you've got a filled circle. Otherwise, you've got a white circle indicating that the values are the same. So when you just inspect closely and try and describe what's happening modulo 4 here, then you arrive at the statement of quadratic reciprocity, which is this equation here. Okay, so let's look at this example in the notes. There's an example at the bottom of page 64. Now, we'll say more about this in due course, but what this quadratic reciprocity gives us is an algorithm for evaluating Legendre symbols. The partial calculation I did with NP on the notes earlier, remember I said the general problem of calculating n mod p reduces to being able to calculate 1 prime modulo another. So here's an example of calculating 1 prime modulo another. So both these numbers are prime. And the aim here is to discover whether 219 is a quadratic residue modulo 383 or not. Okay. Oh, sorry, 219 is not, 219 is not a prime. 383 is a prime, 219 is a constant. 219 factorizes as 3 times 73. 3 and 73 are prime. So we use the prime factorization of 219 and the multiplicative property to get the product of these two Legendre symbols. Then we invoke the principle of quadratic reciprocity. Now 73 is congruent to 1 mod 4. Okay, 72 is a multiple of 4. So 73 is congruent to 1 mod 4. So this Legendre symbol, whatever it is the same value as this Legendre symbol. I can flip it. Okay. Whereas 3 and 383 are both congruent to 3 mod 4. So the value of this Legendre symbol, whatever it may be, is the opposite of the value of this Legendre symbol. So, okay, I've got a different expression. Now, the beauty of this is that when you flip it, you see, when you're facing these guys, the first argument is smaller than the second. So when you flip it, the first argument is bigger than the second. But the Legendre symbol, this first entry is really a congruence class modulo the second number. So we can immediately replace the 383 by its representative mod 3. And we replace 383 by its representative mod 73. So you reduce the first argument modulo the second. So 383 is congruent to 2 mod 3. 383 is congruent to 18 mod 73. So you reduce the first position. Okay, is 2 a quadratic residue modulo 3? Here, the arguments are so small, we can just directly investigate and answer the question. 2 is not a quadratic residue modulo 3. There's only one quadratic residue modulo 3, and that's 1. 2 is a non-residue. Remember, half of the numbers mod 3 are residues, half are not. So 1 is the residue, 2 is not. There's only 2 numbers. So this 2, 3 we know is -1. So we got minus 1 here. So that's fine. So this whole contribution is a +1. What is 18 mod 383? Well, what did we do here? We factorized, we flipped, and we reduced. Those are algorithmic steps which we can keep doing. So when you're looking at you're asking yourself, what is 18 modulo 383? What's the residue status of it? Well, we'll factorize it first. And the idea is you factorize, flip, reduce, factorize, flip, reduce, factorize, flip, reduce. And just like in the Euclidean algorithm where you're doing successive integer divisions, now you're not stuck in an infinite loop because the ingredients to the integer divisions are getting smaller. And eventually they're going to hit 0 and you're going to finish. Well, this is the case here. When you factorize, flip, and reduce, well, the reduce tells you your arguments are getting smaller. So you keep factorize, flipping, and reducing, smaller, smaller, smaller arguments. Eventually they hit the bottom and you can just evaluate them directly. So here we factorize 18 as 2 times 9. Well, 9 is 9 a quadratic residue mod 73? The answer is yes, because 9 is a square. Obviously, it's 3 squared. So that's +1, so you can forget about it. Is 2 a residue modulo 73? Well, that's what we proved yesterday. We proved the residue status of 2 mod 3. It only depends on the residue of the prime mod 4. And 73 is congruent to 1 mod 4, so 273 is plus. I'll take your question in one moment. So we end up with a value of plus 1, which is equal. So plus, this Legendre symbol is plus 1. So it's telling us that 219 is a quadratic residue modulo 383. So it answers yes. So it's a very algorithmic process, and we will fully describe. We'll fully describe and specify the algorithm and get some more practice with it in due course. It's reminiscent to me. It's this kind of a reduction algorithm, downward induction algorithm, just like the Euclidean algorithm. Question.
Line 8.79. Should it be 73 instead of 383?
Shoot. Yeah. 73. So scrub that and make that 73. Sorry, that's great. Thank you very much. Question.
I know you split it into its prime factors there. Would you be able to do that just straight from the 219 and 383, or would you?
So here, for the first step was just to factorize 219.
Could you do 219 and 383?
No. Well, no, because this is a prime. So you're not going to be able to factorize the prime. The starting off question will always be, what's the residue status of this modulo of prime? So you'll never be factorizing the second position. And you only do the flip. You only do the flip move after you've fully factorized the first position. So you got primes in the first. So when you flip it, that will return a prime into the second position. Keep going. So we'll say more about this next time. And what we've got to do now is prove that principle of quadratic reciprocity. We can notice it well enough from looking at calculations, but we'd like to prove it's true all the time. And there's an infinite number of primes, so you'll never prove it by just examining. Okay, thanks for that. I shall see you for more of this next week.